Good evening and welcome to the Maggie and Nick DeWolf Winter Lecture Series. My name is Aaron Harrow. I'm here from the MIT Physics Department, and I'm also one of the organizers of a workshop on quantum computing at the Aspen Center of Physics, which has been on the topic of quantum computing and quantum algorithms, which you might have just heard about at the Physics Cafe. And we've been discussing what we would do with a quantum computer that we hope to build soon. And this, more generally, is what goes on at the Aspen Center of Physics. For the past 50 years, physicists get together, discuss research ideas, bounce ideas off each other, and I'm told there are mountains that occasionally people go to as well. It's a lot of fun. And part of the mission is to advance the research in physics this way, and part of it also is to explain it to people who are not practicing physicists, which is what this lecture series is all about. And so for that, I want to thank the Maggie and Nick DeWolf Foundation and the Wheeler Opera House for letting us use this beautiful space. So there's one more lecture in this series. I'll mention next week is the last one of the winter series. It's about the human body. And then you should look on the Aspen Center for Physics website for information about the next talks will be in the summer. So there's a great series of events this summer, which you should look up on the web. So tonight's speaker we're very lucky to have is my friend and colleague Scott Aaronson, who's from MIT. We're sad to be losing him soon to UT Austin, where he's going to lead a major center of quantum computing. And I think that knowing Scott, he would not want me to dwell on the large number of awards and honors he's received over the years. I'll mention just one, which is the NSF's Alan T. Waterman Award, given out to anyone in science or engineering. And Scott was one of two recipients in 2012 to get it, putting him really at the very top of scientists in the country. I think Scott would want me to instead talk about his intellectual contributions, which are in the field of computational complexity. He's going to tell you about it, about what computers can and cannot do. And his work here is characterized by a combination of, I think, looking at problems very hard, solving deep math problems, but also having fun and playing around with things. For example, one of his contributions was to look at the many worlds interpretation of quantum mechanics, which says that maybe in one branch of the wave function you're here, and in another branch you're still on the ski slopes, in another branch you're doing something else entirely. If you had a quantum computer and you could just pick one branch at the end to and filter out all of the others, something known as post-selection, what would be the computational power of that? And it began as sort of a thought experiment. It led him to make some major contributions in complexity theory, and also to be the basis of what companies like Google are now trying to do to demonstrate that their prototype quantum computers are beyond what classical computers can do. So I think Scott's work is characterized by this combination of having fun and solving important problems. And today he's going to tell us about this mix of computational complexity and interesting problems. And I'm sorry, I went a little out of order. I forgot to mention also that he, if you look at his work, he has a lot of also interesting that he doesn't. A lot of scientists think narrowly, and Scott is, I think, one of the best examples of not being a narrow-minded scientist. And so while computational complexity is often narrowly thought of as something about computers and their capabilities, Scott looks more broadly at its implications for many, many other things. For example, writing a paper called Why Philosophers Should Care About Computational Complexity, where he talks about implications for free will, inductionist logic, and many other topics, including time travel. And so I think tonight you'll get a small taste of what sort of things Scott thinks about. So let's give Scott a hand.
That may be the nicest introduction I've ever gotten. Thank you, Aaron, and thank you for coming, for having me here. I was here 2 years ago for the warm-up act, I guess, the cafe, and so it's really an honor to be here in this beautiful place to give a talk. And so I want to tell you about the connections between computational complexity, which is sort of my field, and the laws of physics. Now, of course, this will involve, as one aspect, talking about quantum computers. When I did a Google image search for quantum computer, this is one of the first things that came up. Now that might be what they look like. So now I'm not an engineer. this will become clear in this talk. They don't let me near the equipment. So I'm not like Charlie Marcus, who many of you heard from. I'm not even a theoretical physicist like Ed Farhi is. I'm a theoretical computer scientist. Okay, so for my purposes, it might as well look like that. Okay, but my starting point is, about just asking about what are the fundamental limits of technology. There are certain things that would be awesome if we had them, and yet somehow we never see them. Warp drive, where is it? We've been waiting for it. The perpetual motion machine, maybe, the only, really sustainable solution to the world's energy problems. And then the third one that I'll mention is what I call the Uber computer. Okay, now, let's be clear, this is not a computer that's going to tell you the meaning of life or, what's the dark matter or, or anything like that. But at least any well-posed mathematical question that you put to it, it would immediately tell you the answer. Okay, so here we see, this computer being asked, is Goldbach's conjecture true? That says, is every even number 4 or greater the sum of 2 prime numbers? Okay, a famous unsolved problem in math. And the computer just immediately says, yes, true, next question. Right, and I think a lot of people have the impression that this is what computers already are. Okay, but they're not. I mean, there remain math departments that actually employ human mathematicians for the time being, because I think the way that they would put it is when most of the math problems that interest us actually involve an infinite number of different cases. And even if you have a computer that's so fast that it can check a trillion cases in a few seconds, well, you've still got infinity to go, right? So in fact, we don't, and there are even many problems that involve only a finite number of possibilities, but such a staggeringly enormous number of them that you could use all of the computers that exist on the Earth today, or scratch that. You could convert the entire galaxy into microchips, that are just doing nothing but working on your problem. And from now until, the heat death of the universe, you would not have made a dent on the problem. Okay, at least, with the algorithms that we know today. Okay, the point that I want to make here is that, in the case of the first 2 machines, we know something from the laws of physics about why they do not exist. Okay, it's not just, some random fact that, the funding ran out before we managed to build them, or, it was too hard to build. Okay, and, in the case of warp drive, we have Einstein's special theory of relativity, which says that, if you could send a signal faster than light, then in someone's frame of reference, you're also sending that signal backwards in time. And then you got to deal with all the, nonsense about you kill your grandfather, and then you're not born, but then therefore you are born, and, it's you don't want to get into that stuff, okay? So, in the case of the perpetual motion machine, there's the second law of thermodynamics that sort of gives us a deep explanation as to why, we can only, maybe approach this as a limit and never actually have it. Okay, now what about the third case? What about the Uber computer? I think that we should really think of it as parallel to the other two, in the sense that we should be asking what are the principles of physics that impose the fundamental limits on what we can and cannot compute. Okay, and can studying those limits actually feed back and tell us something new about physics? Okay, so those are the sort of the questions that I take as a starting point. And then, you sort of have no choice but to talk about quantum computers, right? Because, they're obviously relevant to it. But, to me, if you can build a useful device, I mean, that's a really nice cherry on the sundae. But this is the ice cream, to really, understand what are the ultimate limits. Okay, so I have to tell you a tiny bit about, the world where, the map of the world where computer scientists spend most of their time. And this, if you were at the cafe, Eddie talked about how he had to learn the abstract language of computer science. So this is what he was talking about. We like to organize all the different mathematical problems that a computer might solve into different classes. Okay, that are called complexity classes. Okay, that can be solved with more or less resources, and they have really dumb names. Hard to hard to popularize. I envy the physicists who call everything things like black hole, Big Bang, quark. Those are awesome names. We're stuck with non-deterministic polynomial. That's what NP stands for. But it's really just as good, okay? So P is the class of all the problems, by which we mean like an infinite family of yes or no questions, for which there is an algorithm, running on a completely ordinary digital computer, like the one, in your pocket, probably, that uses a number of steps that grows at most like the size of the problem raised to some fixed power. Okay, that we call polynomial time, if an algorithm has that kind of rate of growth. And we think of that as reasonably efficient, right? What it means is if you double the amount of data you're trying to process, then maybe the amount of time you'll need doubles, maybe it multiplies by 4, but it multiplies by some fixed factor, okay? And so it might grow linearly or quadratically or something like that, with the size of the of the input that you're trying to process. And most of what we do with our computers on a day-to-day basis is in this class. Okay, versions of like multiplying, dividing, sorting numbers, spell checking, all the algorithms that your web browser is using. They all fall into this class. Okay, and and even some very, very non-obvious things like testing whether a given integer is prime or composite. Okay, there's an efficient algorithm to do that. If the number is composite, it gives you no clue about what the factors might be. Okay, if you want the factors, that's a very different matter. Okay. Okay, now NP, this is a slightly more subtle concept. This is the class of all the problems where if the answer is yes, then there is a short proof of that can be efficiently checked, meaning checked by a polynomial time algorithm. Okay, so imagine like a jigsaw puzzle, let's say with no picture on it, right? So you just have 1,000 pieces. You're trying to fit them together. You don't even know whether it's possible to fit them together, a priori, okay? And if it is possible, you don't know if there's only one way of doing it or if there's a million different ways, okay? But at any rate, if someone, who was really, all-knowing wanted to prove to you that it was possible, there would be a very easy way for them to prove it, and just, which would be for them to just sit down and, and do the damn puzzle, right? They assemble it, and, and they show it to you. You've got to say, well, okay, I guess it was possible, right? And a huge fraction of the optimization problems that arise in science and engineering and finance and industry have this problem, have this basic character, right? You have a whole bunch of constraints. Like let's say you're trying you're an airline, you're trying to schedule flights in order to minimize the number of delays. Okay, so what your constraints are. You're trying to get a solution that gets within a certain budget, right? There's maybe an astronomical number of possibilities to check. Okay, but if someone gives, if someone manages to find a better schedule, then they can just show it to you, and you can see that it's better. Okay, so that's NP, and so the factoring problem does belong to NP, because if someone wants to prove to you, let's say that a number has 3 different prime factors, they just have to show you the prime factors. You can multiply them pretty easily, or at least your computer can. Okay, but if it was only given the product, then factoring them would be a much, much harder matter, or so we think. Okay, and then there's this concept of NP hard problems, which are problems that if you had the ability to solve them, then that would let you solve every problem in NP. Okay, so it's at least as hard as all the stuff at NP. And this hierarchy goes up, really, really high, too high to fit on the slide. I have a website I made when I was a student called the Complexity Zoo that has about 500 of these classes. Okay, they, so you can get, like unbelievably high, levels of hardness. Okay, but a particularly interesting class is called the NP complete class. Okay, these are the problems that are both NP hard and in NP themselves. So these are sort of like among all the problems whose answers can be easily checked, these are the hardest ones. These are the ones that if you could solve them, then you could solve every other NP problem. Okay, and that's sort of a weird, definition. It's not even obvious from it that there should exist any NP-complete problems. Okay, so a huge discovery of theoretical computer science in the early 1970s. I think the thing that really started this field was the discovery that there is not just one or two, but thousands of problems of practical interest that all fall into this NP-complete class. Okay, solving a jigsaw puzzle, which I mentioned before, is one example. Coloring a map so that no two neighboring countries, get the same color. If I give you, the Facebook graph, who's friends with whom? Are there, 2,000 people who are all friends with each other? Okay, you can, if you make up a problem involving some huge number of constraints, the amazing fact is it will probably be NP complete, unless it has a really good reason not to be. Okay, factoring is special, okay, which is not unrelated to why we're able to handle it with a quantum computer, okay, which, I'll come back to. But these NP-complete problems, these would really be sort of the holy grail of computer science if you had an efficient method to solve these. And what's amazing is that you would only have to discover a fast algorithm for any one of those problems. And then the whole beauty of NP completeness is that could then be converted into a fast algorithm for all of the others. Okay, and in that sense, all of these different problems, the jigsaw puzzles, the flight scheduling, protein folding, things from every field of like science and engineering, and operations research and finance. In some sense, they're all the same problem. Okay, and in fact, there is a famous, literally million-dollar question that you may have heard of, and this is the question of whether P equals NP. Okay, so, this question is in popular culture. It was on The Simpsons. It was on Futurama. It was even, in various movies, which were not very good, so I won't go into. Okay, but there are 7 problems. That were the Clay Math Foundation put $1 million reward on in the year 2000. It was like the greatest math problems of the 20th century, right? One of them was the Riemann hypothesis about the distribution of prime numbers. One of them was the Poincare conjecture in topology. That one was solved by Grisha Perelman, who then turned down the $1 million prize. Okay, so none of them have actually been awarded yet. Okay, but P versus NP is one of them, and I would argue that it is clearly, obviously, the most important of the 7 problems. Okay, first of all, it's the only one of the 7 with sort of direct practical implications, you could say. Okay, but in addition to that, it sort of encompasses all the others in the sense that if P were equal to NP, what would that mean? It would mean that every problem that was where an answer was efficiently verifiable or checkable would also be efficiently solvable. Okay, I mean, anytime you can recognize the answer, you can program your computer to quickly recognize a good solution to something, you could also program your computer to quickly find a good solution whenever it existed. It would mean that there would be a way to cut through the brute force, enumeration of one possibility after the other, and just, go straight to the solution whenever it existed. Okay, and and one thing, that would mean that essentially, all the cryptography that we use today would be broken. Even the kinds that aren't broken by quantum computers. It would also mean that, in this case, we could really put human mathematicians out of a job, right? Because we could, in fact, we could program our computers to solve the other 6 clay problems for us. Okay, why is that? Well, because the problem of checking whether a given mathematical proof is valid, if you write the proof in a hair-splitting enough way, right? That is something you can program your computer to do, right? And there's a whole field called formal verification where people have their computer prove that that this airline, that this airplane control system, is not going to crash or whatever, right? They prove that as a mathematical theorem under stated assumptions, right? And and a computer can actually check a proof. The issue is, there may be a huge number of proofs. It may be very, very hard to find one. But if P equaled NP, you could say to your computer, look, is there a proof of the Riemann hypothesis in this formal language, which is at most 1 billion symbols or fewer? Let's say, right? And if a proof exists, if such a proof existed at all, then your computer would be able to find it, and in time that would grow, maybe like 1 billion, maybe like 1 billion squared. Okay, but at any rate, it would grow as a polynomial function of the size of the proof itself. Right, and so the only way, that your computer wouldn't solve the problem would be either if there were no proof, or if the proof were just, too large to be written down at all, you might say. Okay, so this was actually, as far as we know, was first noted by Kurt Gödel. Some of you might know as the incompleteness dude. Okay, but he was, a logician, maybe the greatest logician of all time, and was ahead of his time in many ways. In 1956, he sent a letter to John von Neumann, who at that time was dying in a hospital, and said, "I hear that you're getting better." So unfortunately, he wasn't. But since you are, let me take the liberty of troubling you with a mathematical question. And he then asked what today we would immediately recognize as the P versus NP problem, although it was not, although no one published about it for another 20 years. Okay, and he said, look, if there actually were a machine that could decide, that could find proofs of length n, with a number of steps that grew only linearly with n, or even only quadratically with n, this would have consequences of the greatest magnitude. He goes on to say, it would mean that the mental effort of a mathematician could be completely replaced by machine. And then he puts in a footnote, apart from the postulation of axioms. Okay, so this is really what we're talking about. It's a practical question, but I think it's also almost a metaphysical question. Okay, that's P versus NP, and you could spend your entire life just thinking about this as a pure math problem, and people do, and that's a whole nother talk that I could give, right? What progress people have made toward answering this sort of question, why it seems staggeringly difficult. I think that eventually, if civilization lasts long enough, which is, my main uncertainty, I think, eventually, sure, we could answer this sort of question. It, might merely take some hundreds of years, but we could also ask, is P versus NP really the right question, right? It's a pure math question, and so in order to even ask it, you need some kind of mathematical model of what you even mean by a computer, right? What you mean by a computation, what you mean by its being efficient. And so, computer science has had, an answer to, what we mathematically mean by a computer since the work of Alan Turing in the 1930s, which, many of you may have heard of, if you saw that movie, it wasn't quite right, but, maybe you sort of got the idea. Okay, he was, he broke the, German Enigma code, or was one of the key players in breaking it during World War II. Okay, but, his other career, one of the other things that he did was to come up with the mathematical formulation of what we mean by computation, which in some sense has not changed from the 1930s until today. Okay, and not even quantum computing challenges it, by the way. Okay, but now, if we ask about efficient computation, that's another story. Okay, so we've had a computer scientists have had a notion of what they mean by a fast algorithm or an efficient algorithm since the 1960s. And that's tied into a belief which is called the extended church-Turing thesis, or ECT. So, I put it on a parchment because it's that important, okay? But the church-Turing thesis basically said that what is computable, let's say by us, or, you could say by any device in the physical universe, corresponds to what can be done on this mathematical idealization that's called a Turing machine, which is like this infinite paper tape and this, state machine that goes back and forth, writing and erasing zeros and ones. Okay, now the extended version, the one from the 1960s, says that what can be done efficiently in the physical universe corresponds to what can be done, efficiently, by which, our rough and ready approximation is in polynomial time by a Turing machine. Okay, so it says that Turing machines capture what can be efficiently computed in the physical universe. And and maybe I'm already here. I'm going to put in like a weasel phrase. Maybe Turing machines enhanced by random number generators. Well, we don't think that really helps, but we can't prove that it doesn't. Okay, so. Okay, but now, this is not a mathematical thesis. This is I personally would view it as an empirical claim about the physical universe. I don't think that's how Church and Turing themselves saw it, but, I apologize to them. Okay, I view it as a claim about what kind of devices we could build in the physical world. So it behooves us to ask, how sure are we of this thesis, and what would a challenge to it even look like? So long before we get to quantum computing, there's been a long history in computer science of other ideas as to how you could exceed the limits of what a Turing machine can efficiently compute. Which means, just to explain, like all the computers that we have today, your laptop, your iPhone, a Cray supercomputer, a Google cluster, sometimes they're all different versions of the same slop, right? They're all just, Turing machines in different clothing. Okay, but yeah, what would it mean to have a device that maybe a million times faster or a million times slower, but that doesn't change their fundamental nature? Okay, what would it mean to have a computing device that really was different in its fundamental nature? All right, well, let me, just warm up to quantum computing with some easier to understand ideas. Okay, so here's a really old proposal. Okay, you take two glass plates. And in between those plates, you put pegs in whatever configuration you want. Okay, and then you dip the resulting thing into a tub of soapy water, and then you take it out. And you look at, and what will usually happen is that soap bubbles will form, sort of connecting the pegs together. And, if you know anything about bubbles, right, they like to minimize their surface tension. They like to, which in this case, will typically mean minimizing the total length of bubble, sort of connecting the pegs. Where where these sort of or we could just say minimizing the total length of line segments connecting the set of points in the plane, where two line segments can also meet at intermediate points like these. Okay, so this is actually a well-known problem in geometry and combinatorics. It's called the minimum Steiner tree problem. Right, where I give you like a set of cities, if you like, I ask you, what is the minimum amount of wire that you would need to connect all these cities together on the internet? Okay, and these cities all have just x, y coordinates in the plane. Okay, now here's what's crazy about this. Okay, the minimum Steiner tree problem is very well known to be NP hard. Okay, now what I just told you is that, bubbles, because they like to be in their lowest energy state, or they're, minimize their surface tension, they should just find the minimum why not, solve NP-complete problems this way, right? Can a tub of soapy water do what our fastest supercomputers cannot? Okay, why not, so like NP-completeness tells you that you could create a configuration, of some billions of, of pegs probably, but not an impossible number, such that if you knew the smallest length of bubble connecting those pegs together, then from that you could read out, for example, your friend's cryptographic private key, okay, or maybe your enemy's key would be more likely, okay, or you could read out, a proof of the Riemann hypothesis, okay, you could, many of the secrets of the universe would be laid bare to you, okay, and so this seems, kind of implausible, right, and so, there was a discussion on the internet some years ago when, someone was saying, well, look, I don't think it works because, systems in nature like to minimize their energy, but they won't always do it, right, like if you had a rock on some crevice on a mountainside, it could reach a lower state of potential energy by rolling up first and then rolling down. But it's rarely observed to do that. Okay? So why shouldn't these bubbles get stuck in, what we call, local optima, metastable states? Okay, and then someone else said, well, this is just a computer science party line, but not one of you has ever, actually tried the experiment. So this led into the one foray, I guess, into experimental physics in my career. Wearing the gloves because I cut my hands on the glass. I should have used plexiglass, I think. But, so I tried it out. With 5 or 6, pegs, it usually works. It's a great science fair project, But when you start putting in more pegs, you find you don't always get the global optimum. In fact, sometimes you get something that's not even a tree, like it has some intermediate cycles of bubble in it, which then, proves that it cannot be minimal. Okay, so I didn't try every possible brand of soap, but I think we have some initial evidence that soap bubbles are not solving NP-complete problems by magic, right? And and there's lots of other, you'll read, like if you read the science press, every year or so you'll see someone saying, well, what about proteins? Proteins just, try every possible combination, and so they could, solve every cell in your body could be solving NP-complete problems, or or someone has an idea for an analog device that will solve NP-complete problems. Okay, in essentially every case, the answer is it gets stuck in local optima. Sorry, it doesn't work. So, all right, but now let's go, further into physics. Okay, so forget for now about quantum computers. Why not, the other great theory of the 20th century? Why not a relativity computer? Okay, so the idea of a relativity computer would be very simple. You start your computer working on some really hard problem. You leave your computer on Earth. You then board a spaceship. You accelerate to very, very close to the speed of light. And then you decelerate, you return to Earth. Now, Einstein tells us that in Earth's frame of reference, billions of years will have passed. Probably, all your friends will be dead. Civilization will have collapsed. Okay, but if somehow you could still find your computer, if let's suppose that we're somehow still running, you'd get the answer to your hard problem. Okay, so so this immediately raises a question, which is, why doesn't anyone try this? Right? I mean, if you were worried about your friends, we'll just bring them with you on the spaceship. Is there any, again, the question is not, does it sound silly? Does it, whatever. The question is there anything in the laws of physics themselves that rules this out? That rules out that you could get unlimited computation power just by using relativity? Okay? And the very interesting answer is that there is. Okay, and I think that the answer really has to do with the amount of energy that it would take to accelerate to this close to relativistic speed. Okay, what you can argue is that if you wanted, say, an exponential computational speed up, then you would have to accelerate so far that the difference between your speed and that of light would be exponentially small. Okay, but to do that would require an exponential amount of energy, which means that even before, liftoff, you're going to spend an exponential amount of time just fueling up. right? So it's like it's very, very interesting when you can take some laws of physics and they look like they let you solve NP complete problems, give you these other superpowers, but when you take into account all the other things that we know about the laws of physics, then nature seems to prohibit us from solving these problems too efficiently, right? Just like with all these ideas about perpetual motion machines, many of them almost look like they work, but there's always something more about physics that that prevents it from working. Okay, so a related idea is what I'll call the Zeno computer. Okay, and this is simply a computer that would do the first step of its operation in 1 second, next step in half a second, the next in a quarter second, the next in an eighth second, and so on. So that after 2 seconds, it would have done infinitely many steps. Right? Again, sounds like a great idea. Why doesn't anyone try it? One answer is that people do try this. There's a community of people who overclock their microprocessor, which means they run it faster than the recommended speed. Okay, now there is a danger in doing this. If you run a microprocessor too much faster than you're supposed to, it will overheat and it will melt. Okay, and by the way, this is why your computer has a fan. Okay, and there have been supercomputers that were cooled using liquid nitrogen or things like that, so that they could be safely run faster. Okay, but now you can calculate that as you wanted to do more and more, say ops per second, run the computer faster and faster, you would need more and more energy. Initially you could say more and more energy for the cooling system. Once you get to fast enough, then there's just energy in the computer itself cycling through that number of states. Okay, and and you can ask, is there a fundamental limit? Well, as far as physics currently knows, there is. It's a limit that was actually discovered by Max Planck in 1900, although he wasn't thinking about computers. Okay, and what the limit seems to be is that if you ran your computer so fast that you were doing, say, 10 to the 43 operations per second, okay, about 1 operation per Planck time, as we call it, okay, which, that's very fast. That's many orders of magnitude beyond what we can do today, but that's a finite and known number. If you wanted to run your computer so fast, you would need so much, the calculations say that you would need so much energy concentrated in so small of a volume that your computer would exceed what's called the Schwarzschild radius. Okay, what that means is that your computer would collapse to a black hole. Okay, which I really like as nature's way of telling you, not to do something. Okay, so all right, so we could talk about time travel computers and all kinds of other things, right? But what about quantum computing? You knew it was coming at some point, and if you heard about spins, these are some happy spin 1/2 particles. That's what they look like. Quantum computing on its face, sounds about, almost as outlandish or as science fiction-y as the relativity computer or the Zeno computer and so on. But of course, this is something that there are many, groups all over the world who are actually working to build right now. And, so what's the idea here? So we first have to say, what is quantum mechanics? And I'll do this in one. I know that, Ed Farhi and Charlie Marcus would have different answers than me as to what quantum mechanics is. My perspective as a computer scientist is that quantum mechanics is actually an incredibly simple thing once you take the physics out of it. Okay, it's in some sense it's like quantum mechanics is barely even physics. It's a set of rules. It's like an operating system that that our known laws of physics run on as application programs. Okay, and what it really is it's just a certain generalization of the rules of probability themselves. Okay, in probability, you talk about, let's say there's maybe a 30% chance of rain tomorrow, or 70% chance, or, maybe this cat is dead, maybe it's alive, you don't know, so you assign probabilities, and then you look, and you see, so then you know, right? But one thing you would never do is you would never say there's a negative 30% chance of rain tomorrow. Okay, that would just be stupid, right? Or or there's a or even less so that this cat has a square root of -1/2 chance of being dead. Right? But in quantum mechanics, you do something like that, okay? Because what it fundamentally says is that to describe the state of a physical system, you have to take every possible configuration that you could see that system in on measuring it. Like, is the electron spinning up or is it spinning down, so forth. And each configuration has to be assigned a number called an amplitude. Okay, and amplitudes can be positive or negative. In fact, they can be complex numbers. And and you use amplitudes to calculate probabilities. Okay, but the amplitudes themselves work very differently than probabilities do. In particular, they can, if something could happen one way with a positive amplitude and another way with a negative amplitude, then those two ways could, as we say, interfere destructively and cancel each other out, with the result being that that thing never happens at all, right? And in some sense, everything in quantum mechanics for the last 90 years has just been different manifestations of that one phenomenon, okay, the interference of amplitudes. But it was not until the 1980s that a few physicists like Richard Feynman and David Deutsch had the seminal idea. To simulate a quantum system with our existing computers, like a high temperature superconductor or something like that, or a complicated biomolecule, that's very, very well known to be an extremely hard problem. Okay, and the reason is you've got to keep track of this entire list of amplitudes, and the number of amplitudes grows exponentially with the number of particles in your system. Okay, each particle could double the number of amplitudes. Okay, and so just to keep track of like 1,000 measly particles, quantum mechanics says that nature somehow has to have some scratch paper where it's storing 2 to the 1,000th power complex numbers. Okay, that's to me that is the most staggering thing that quantum mechanics says, right? And then but then what Feynman and Deutsch asked is, why not? If that's really true, then why not put it to work for us? Right? Why not build a computer that itself would exploit this phenomenon of interference, that itself would be described by a superposition with exponentially many amplitudes. Now, supposing that we built such a computer, what would it be good for? Feynman was only able to give one answer to that question, which is it would be good for simulating quantum physics. Which I think if we actually get quantum computers, that will likely be the most important real application that they have. Quantum computing has become much broader than that. It's become a field about what can you do if you have 2 to the n complex numbers working for you. Now I got to ward off a misconception that if you read almost any popular article that's been written on the subject, they'll say a quantum computer is just a computer that can try every answer in a different parallel universe. Right, and we would write it with a notation like this: that for each possible answer to your problem, you would have some amplitude for it. Okay, and this is just the notation we use for that. Okay, and so there's some sense in which that's sort of true, right? That you can create a superposition over all possible answers. Let's say to an NP complete problem. Okay, that's quite easy to do with a quantum computer. The hard part is, at some point you've got to measure the thing. Okay, at some point you've got to look at the computer, read out a state. And if you just measured a superposition over all answers, not having done anything else, what you would see would be a random answer. Okay, and of course, if you just wanted a random answer, well, you could have picked one yourself with a hell of a lot less effort. You could have just flipped a coin a bunch of times, okay? So, the only hope of getting a benefit from a quantum computer is if you can take advantage of this phenomenon of interference between positive and negative amplitudes. If you can take advantage of the way that amplitudes are different from just ordinary classical probabilities. Okay, if you can choreograph a pattern of interference where for each wrong answer, some paths that lead to it have a positive amplitude and others have a negative amplitude, so that on the whole they cancel each other out. Whereas the paths leading to the right answer should reinforce each other. Okay, that's like a really, really weird hammer that physics gives you. And people spend a long time searching for a nail that it would hit. Okay, so you can in computer science we can give anything we like an inscrutable sequence of capital letters. Okay, so my advisor Umesh Vazirani and student Ethan Bernstein in 1993 defined BQP, bounded error quantum polynomial time, as like the quantum generalization of the class P. Okay, and then the question becomes, how large is BQP? And does it contain any problems that are not in P? Okay, the breakthrough here, as Farhi mentioned, came in 1994 when Peter Shor discovered that the factoring problem is in BQP. Okay, in other words, if you built a quantum computer, you could efficiently factor numbers. Okay, this made many people excited about quantum computing who hadn't been before. Okay, so here's a rough map of the world. I showed you P and NP complete. BQP, we're still trying to figure out exactly where it fits in. I drew it with these wavy borders because everything quantum is spooky and weird. But we know that BQP contains factoring. We know that it contains at least all of ordinary P. We don't think that BQP contains the NP complete problems. So we don't think it contains all of NP. That's an extremely important question that I'll come back to. It seems to capture certain problems like factoring that lie in this intermediate zone between P and NP complete. Okay, and these problems tend to have very, very special structure. Like factoring has really special properties that make it very useful for cryptography, more so than any known NP complete problem. But alas, those same special properties are what Shor was able to exploit to give a quantum algorithm to break the problem. Okay, and then there might be problems that are in BQP, but that are not even in NP. So that where a quantum computer could solve it and a classical computer could not even check the answer. The only way to check it would be use a second quantum computer. Okay? All right, so an obvious question is whether quantum computers can actually be built. You may have heard where we are now after maybe $1 billion or so of investment in the field. I'm proud to say quantum computer has factored 21 into 3 times 7 with high statistical confidence. I think 35 is on the horizon. We understand very well the difficulties in scaling this up. Okay, the problem is decoherence. The problem is as soon as you look at a quantum state, you measure it, which means you just you force the amplitudes down into ordinary probabilities. And your state, which was previously a superposition, just reverts to being, snaps to being just one possibility or the other one. And a measurement could be like any stray particle that passes through your computer. And, so what that means is that you need to keep, if you want to do a quantum computation, you have to keep your device incredibly well isolated from its external environment. But then at the same time, you need to go in and do the operations you want. Okay, and this is certainly a very, very hard engineering problem. People have made tremendous progress on it, on how to control qubits. And I'm very excited that in the near future, we may be able to do something, if not something useful, then at least something that for a classical computer would be hard. Okay, but now there are some skeptics, who think that this is just not possible at all. That the entire thing is a big boondoggle, right? My answer to them has always been, well, I don't think they're right, but I hope they are. Because if they are, then wow, we'll have to rewrite all the physics textbooks. That's way more exciting than if a quantum computer merely can be built. Okay, because that changes the rules. Right? Believing that quantum computers can be built is just a conservative option. Okay? It's the one that makes no change to existing physics. Okay? And so I think the goal is either, build the devices or else, discover some new principle, along the way that, that would explain why they couldn't be built. For me, testing quantum mechanics in this whole new regime, is really the biggest reason to build quantum computers. You could say, what I care about more than factoring, more than quantum simulation, is just disproving my friends who say it's impossible. All right. Now, key point, as I said, factoring is not thought to be NP complete. We don't think that there's a general quantum algorithm to solve all the NP complete problems. Now, we can't prove that, which is not surprising because we can't even prove that classical computers can't solve these problems. That's the P versus NP question, right? So how on earth would we be able to prove that quantum computers can't do it? Okay, but we do know that if there's a quantum algorithm for the NP complete problems, it will have to look very, very different from any of the quantum algorithms that we know today. Okay, and we have theorems about that. Okay. Now, there's one very famous proposal which Farhi and others came up with around the year 2000 for a quantum algorithm that would try to exploit NP-complete problems by using their structure as in a detailed way, as you would really have to if in order for it to work. And this was called the quantum adiabatic algorithm. Okay, and it's if you've heard of like heuristic search methods like genetic algorithms, or especially if you've heard of something called simulated annealing, these are approaches like for a classical computer that you can throw at an NP-complete problem. There's no guarantee that they're going to work, but they might work. Right? They'll start with a random answer and then they'll slowly improve it, to get, if not the optimal answer, then at least hopefully a pretty good one. Right? And so the adiabatic algorithm is like a quantum version of that. Okay, and so it's it involves transitioning between two different Hamiltonians, where if you transition slowly enough, then the final Hamiltonian, which just means some operation that you apply to your quantum computer, has a ground state, which you'll be sitting in, which will encode the answer to an NP-complete problem of your choice. Okay, now some of you may have heard there's a company called D-Wave, which was on the cover of Time magazine. They've spent hundreds of millions of dollars so far to try to build very, very special purpose quantum devices that are just optimized for something like this adiabatic algorithm. Okay? But now, there are several problems with this approach, right? One is that, we don't have devices yet that we think are good enough to really see a quantum advantage if there is one, right? And the experimental results on the D-Wave device show that it is not yet sort of getting a scalable advantage over the best classical algorithms that we have. Okay, which is consistent with what many of us predicted since the beginning. Okay, but then a second issue is that even if we could build a perfect quantum computer, we think that there will be cases where even this adiabatic algorithm will need exponential time to solve the NP-complete problem. Okay, and the amount of time that this adiabatic algorithm needs is controlled by something called the spectral gap, which is like a gap between two different energy levels. And if the gap between these two things becomes exponentially small, it means you've got to run the algorithm for exponential time. Okay, and when people try it out numerically, what they find is that, very, very often, when you're dealing with a hard NP-complete problem, there will be just one point where these two energy levels almost kiss each other, but not quite. And because of that one point, you have to run the algorithm exponentially slowly. So, I hope that Eddie, if he's here, doesn't mind my sharing. He has, a wonderful story that he tells that, he went to an expert in condensed matter physics who had, decades of experience in calculating these eigenvalue, these energy gaps for physics reasons, and said, look, based on your experience, do you think that in our algorithm that this energy gap is going to decrease polynomially or exponentially as a function of the number of particles? And the expert thought about it. He said, I think it will decrease exponentially. Okay, and that was not the answer that Eddie wanted to hear, obviously. So he said, why? What's the physics reason for thinking that? And he thought about it more, and he said, well, it's because otherwise your algorithm would work. Okay, so I think that there's something very, very deep here, right? Which is that after you've seen enough examples of nature not solving an NP-complete problem, you might be tempted to just elevate the hardness of NP-complete problems to a fact of the physical world, like the impossibility of faster-than-light communication. And you might then say, okay, suppose I adopt that, then what are the implications of that for other things? Can I explain other things on the basis of that presumed impossibility? Okay, so I had some other slides which were about, I think a really striking application of complexity to fundamental physics, in particular to what's called Hawking's black hole information problem. But unfortunately, I'm out of time. So what I'm going to do is I'm going to just whet your appetite with some, awesome pictures. Okay, you can look at my awesome my mad PowerPointing skills. Look at that. That's called the black hole firewall. Okay, and this is how computational complexity and the limitations of quantum computers turns out to be very, very deeply related to why it is that how it is that information can come out of a black hole. Things like that, which is an incredible story, one that just developed within the last 3 years. Okay, it's been connected even to string theory, to what's called wormholes and the ADS-CFT correspondence, complexity, and our beliefs about the limitations of quantum computers are showing up even here. And this is what some of my recent research has been about within just the last year or two. And if anyone wants to ask me questions about it, I can tell you more about it. But I think to be polite, I'm going to wrap up at this point and just say, for a conclusion, that my proposed research agenda is, well, for starters, prove P is not equal to NP. Okay, then prove that not even a quantum computer could solve these NP-complete problems efficiently. And then, or build a scalable quantum computer. Or even more surprisingly, explain why you couldn't. Clarify whether all of known physics, the standard model of elementary particles, general relativity, and so forth, can be simulated by a quantum computer. What about string theory and so forth? And then can you turn things around and use ideas from computational complexity or our beliefs about what not even quantum computers would be able to do to get new insights about physics? And I think the evidence of the last few years seems to be that you can. So let me stop there. Thank you.
So thanks, Scott, for a great talk. And we have time for some questions from the audience on any topic related to it or unrelated.
Yeah.
Can a Turing machine emulate the quantum computer?
That's an excellent question, and the answer is yes. A Turing machine can emulate a quantum computer just very, very slowly. Okay, so here's what you can do. If you want to simulate a quantum computer using a classical computer, right, you can program your classical computer to just store the entire list of amplitudes, right? Just store this entire list of 2 to the n complex numbers, right, for n particles, and then update it whenever something happens to the particles. Now that will be an exponentially slow simulation. Right, but in principle it will work, and and if the number of particles is small enough, then it will work. So just this morning at our conference, we had a talk by Dave Wecker of Microsoft, who has actually created a software for emulating real software. You can download it for emulating a quantum computer on your home computer. It's called Liquid, the program. Okay, and it can simulate Shor's algorithm, the factoring algorithm, like to factor 35 into 5 times 7, for example. It takes about 2 minutes to do that. Okay, so it's slow, right? And if you wanted to simulate the factorization of 91, that might take a much longer time, right? So it's really, really slow, but eventually it will do it. So you could say, this is another way of saying that quantum computers do not challenge Alan Turing's original 1936 thesis about what is computable. Okay, the thing that they do challenge is the 1960s thesis about what is efficiently computable. Okay, so they give you the same set of computable problems, but for certain computable problems, we think that they could solve them much, much faster than our existing computers could solve them. Yeah.
Are there other theories with quantum computers
absolutely. I mean, so I should say that a quantum computer can be built, I mean, just like a Turing machine, you could physically realize it using vacuum tubes, as people did in the old days, or using transistors, or, with silicon, or maybe gallium arsenide, or you could implement it using light bouncing around mirrors. Okay, you could even build a computer out of levers and pulleys, or out of billiard balls. Okay, so the underlying logic, is what how the ones and zeros and how they get manipulated is really the thing we care about in computer science, not the physical substrate. Right? And with quantum computers, there's a similar story. You could have a qubit, which is an electron that could be spin up or spin down, or a superposition. But your qubit could also be an atomic nucleus, which is, you could use its spin state, or you could use the polarization states of a photon, or you could even have a qubit, which would be billions of electrons, which are in a superposition of flowing in one direction and flowing in the opposite direction through a coil. Okay, that's what happens in superconducting quantum computing, which is one of the main proposals today. That's a way, way bigger physical system, okay, and yet it implements exactly the same logic of a qubit. Okay, so they're all different possible physical systems that all lead to, the same math for me to think about, for us computer scientists to think about. Just like, all different computers, Macs and PCs, or even a billiard ball computer would lead to, the same questions about algorithms, at the end of the day, for the same P versus NP problem and so forth for us to have to deal with. Mm-hmm. Yeah.
The biggest advances in computers over the next 20 years is it storage, processing speed, algorithms, or some other thing?
I don't know. I mean, I have friends who think that within 20 years there's going to be a singularity and we'll all just be uploaded, into the cloud and live forever. To me, I can't say that that's impossible, but that time scale does seem a little aggressive to me. I mean, although, computers did just beat the best human at Go, right? So I mean, it is, I try to stay out of the field of forecasts, especially when they have specific dates attached to them. Okay, I try to talk about general principles. But that way no one can come and tell me I was wrong. Okay, one important thing to say is that we know for sure that Moore's law cannot continue forever, right? And by some ways of defining Moore's law, it's already broken down, right? Or it stopped about 10 years ago, right? And and so people deal with that by adding more and more cores. Okay, but of course there's also ultimate limits to how many cores you can add, right? As you make your computer and its memory bigger and bigger, you have more and more latency, just because the speed of light is finite, right, to get signals from one part of your computer to another. Okay, so, and then ultimately you have the problem of the Planck scale, where, you can't, make things bigger or denser without your computer collapsing to a black hole. Right? So, we're very far from that, but that proves the point that, there is a fundamental limit to these things like Moore's law, right? And so what's so interesting about quantum computing to many of us is that it just, it goes in, it just completely evades those limits by going in a completely different direction, right? Like for quantum computing, it doesn't matter if Moore's law ends. We will still be able to use a quantum computer to factor 100,000 digit numbers, because the quantum computer is just exploiting additional laws of physics that our existing computers were sort of not even sensitive to. Yeah, sure. Yeah, there you go. Huh? Yep. So if there is a large gap, then you can run this that's correct. You're right. Then you can run the adiabatic evolution, and you only have to run it for a polynomial amount of time, and you will end up in the ground state of your final Hamiltonian. That's right. But you can always just try it out and see what happens, right? And if it works, then you can say, okay, well then I guess my gap was large enough for it to have worked. Right, and then you can also, what people do is they try to estimate these gaps either numerically or analytically. That's often a very hard problem, but we know that there are cases where the gap decreases exponentially. Right. Well, I mean, there are theorems that you can prove. Like you can prove, okay, if your fitness landscape looks like this, then the gap is, 1 over exponential. If it looks like that, then it's 1 over polynomial, right? And these are actually subjects of active research. In fact, at this very workshop that I'm at, we had a lecture about this, okay, with new results about this, okay? So there are theorems you can prove that cover various cases. But we don't have like a master theorem that tells you what would be the gap in any possible case. Okay, and so so unfortunately, this is a much murkier situation than for Shor's algorithm, right? Like Shor's algorithm, you build the quantum computer, and then we know exactly what you should do, how long it will take. If the laws of physics are what we think they are, then it will work. Right, the adiabatic algorithm, there may be no, and if you really want to know, like, is this useful in practice? Does this give you a speed up over the best classical algorithms? For optimization problems that people care about in the real world, there might be no way to really answer that question without just building a quantum computer and trying the damn thing out, unfortunately.
That might be a good note on which to thank Scott again for a great talk.